Collision-free operation is a fundamental requirement for multi-robot coordination tasks, such as formation control, payload transport, and autonomous navigation. With the growing interest in AAM applications, developing a scalable, low-altitude air traffic management system is an urgent need. AAM operations are expected to be large-scale, ad hoc, on-demand, and dynamic. In current aviation today, we have airspace separation, centralized air traffic control, protocols, and collision avoidance controllers on board commercial airlines. However, when we enter the era of advanced air mobility, there is a high chance that some of these layers will not be as effective as before. There might be multiple operators in the same airspace, or the protocols might fail if there is a third agent. In our work, we present a layered safety architecture which integrates a CBVF with multi-agent reinforcement learning. We train using curriculum learning to balance exploration and safety and demonstrate effectiveness through hardware experiments and simulations. In this work, we use a model-based safety certificate function called the control barrier value function, which provides rigorous safety guarantees. However, traditional approaches generally offer rigorous guarantees only when a single safety constraint is considered. With multiple nearby agents, resolving a constraint between two agents may conflict with a constraint involving a third agent, creating a severe gridlock. The inability to simultaneously satisfy all constraints can make collision inevitable. The intersection of the safe sets corresponding to individual constraints does not necessarily represent the true safe set, and this gap is referred to as the leaky corner. Unfortunately, identifying leaky corners without recomputing reachability analysis remains an open problem. Let's define a few parameters for our ego agent, starting with collision distance and the potential conflict range. Here, we see another agent within this potential conflict range in active engagement for collision avoidance. However, if more than two vehicles are within the potential conflict zone, we cannot guarantee safety anymore. First, our method uses a safety-informed graph neural network as the MARL policy to avoid potential conflict regions. Second, a prioritization module evaluates the CBVF values and picks the pair with the highest collision risk. Third, the safety filter modifies the action to prevent potential collision. In our hardware experiments, we have quadrotors navigating to goals after passing through two waypoints. We compare the results of the safety blind MARL to our approach. Notice how the yellow agent missed the waypoint and had to return all the way back. In our approach, the yellow agent waits till the waypoint becomes available, preventing conflicts. We also perform simulations of an air taxi merging operation scenario using an air corridor to San Francisco. Here, we compare the performance of the safety blind MARL to our proposed safety informed approach. Notice the lower time taken and the number of near collisions becoming lower. When comparing other performance metrics like goal reaching rate and near collision instances, our method outperforms other model-based and model-free methods. Our method generalizes better, especially with higher number of agents. To summarize, we integrate MARL with CBVFs. MARL learns to proactively navigate potential conflicting constraints while optimizing for task performance. At the same time, MARL performance benefits from a safety-informed reward signal which guides learning towards safer and more effective behaviors. As a result, our approach enhances both safety and performance to a level that neither safe control methods nor MARL alone could achieve for safety-critical settings.